Can you start, sir?
We can start it. We can start.
Thank you, sir. Good morning. Welcome for the day 5 session 2 of NAMPET sponsored short-term online course on power electronic converters applications in microgrid and vehicle technology from 20th July to 24th July 2022, organized by Department of Electrical Engineering, National Institute of Technology, Odisha, India. It's an honor and privilege to read the biodata of Mr. Brijesh P. Sir. Brijesh P. Sir received the BTech in Electronics and Instrumentation from Cochin University. He is having 14 years of experience in power electronic group of CELAC Trivandrum. His area of interest includes synchro phases, wide area monitoring, microgrids, digital hardware, firmware design of power electronics, and power system applications. He is involved in the projects like development of synchronized phase measurement unit, implementation of wide area monitoring system, grid interactive solar power plants, implementation of microgrid for Indian villages, intelligence sector network for distribution grid monitoring and control. Presently, Brijesh P. Sir working as scientist joint director in the power electronics group CELAC Trivandrum. I heartily welcome you, sir, for the session. Thank you. I request Brijesh P. Sir to hand out the session.
Yeah, very good morning all. Thank you for the invitation and the kind introduction. Myself Brijesh from Power Electronics Group of CELAC. Can you see the presentation screen?
Yes, sir, it will be visible.
Okay. Once again, very good morning all. Actually, I am from Power Electronics Group of CELAC Trivandrum. Today my topic is Power Electronics interfaces in microgrid application. Actually, I will share some of my experience, our team's experience in the implementation of our microgrids in various our NAMBET projects. Actually, I got opportunity to part of NAMBET from its phase 1 onwards. Now we are in the phase 3 of NAMBET. In different NAMBET projects, we evolved different types of we developed different types of microgrids, and actually we try to put everything in actual site. So today I think I can share our experience in what are some of the practical aspects in selection of our hardwares for the microgrid application. Basically, selection of our hardwares in any application, especially in microgrid application, it's dependent upon what is your application and what is your expertise and the time you are having for the project, and also the availability of subsystems and submodules. So I can share some of our experience in that case. Before going to the presentation, a brief introduction about CELAC. CELAC is a premier R&D center of Ministry of Electronics and Information Technology, Government of India. We are a multi-locational, multi-activity R&D organization. Our headquarters is in Pune. CELAC Trivandrum is especially working on the hardware domain. Coming to CELAC Trivandrum, we undertake application-oriented R&D in electronics and software domain. Then even in CELAC Trivandrum, we have different groups which is working in different areas of electronics and software, and belongs to the Power Electronics Group of CELAC Trivandrum. We have other groups like control and instrumentation, broadcast and communication, and hardware design group. and software training division, and strategic electronics group who is working with defense oriented projects and all.
Uh,
So
uh,
even in
Sir, can you make it full screen, sir?
uh, is it not full screen?
No, sir, it's not full screen, sir. It's still in the presentation slides only.
No.
So not yet, sir.
So please click on the slideshow, sir. In the bottom, you can see that.
Actually, it is in slideshow only in my PC.
I think it has not enabled, sir. Please
Still, it
try
is
it
not.
once again. No, sir. Please try it once again, sir.
Okay, sir. You please carry on. Actually, sometimes some network issues are there. That's why it is showing like that. No issue, sir. When
Actually,
it
my
will be,
PC,
okay, then
my PC it is in
yes, sir.
slideshow.
Now slide.
Yeah.
Yes, sir. No problem. It's sometimes some network issue. You said please carry on. No problem from my end.
Okay, we'll tell.
Yes.
Actually, even in our power electronics group, we have different domains. We are in renewable energy domain, especially in solar. Then we are into real-time simulation domain, and HEV domain, and also we are in power quality domain. So we are in a different working in different domains of power electronics and power system. Uh, and you may be aware of the program NAMBET, National Mission on Power Electronics Technology. Currently, it is in phase 3. It is a government of India initiative to strengthen the power electronics R&D in the country. So under the NAMBET, we are having so many sub projects. Microgrid is a domain in that area. So coming to the topic microgrid, I think last 3 days you may be hear the name microgrid, and you may be very familiar with the microgrid now. Anyway, uh, we can define microgrid in our own way, but as per IEEE standard, microgrid is a group of interconnected loads and distributed energy resources with a clearly defined electrical boundary. That's boundary is well defined, and it can act as a single controllable entity with respect to the grid, and either it can operate as a standalone system, or it can connect to grid, and it can operate in the mode of grid connected mode. So a microgrid is having different energy resources may not be it is not may not be all our renewable resources. You can have even fossil fuels in the microgrid, but we are mainly focusing on the microgrid with the renewable resources. So important thing is microgrid is connecting to the our grid at a single point, so it can work in two modes: grid connected and islanded mode. This is the basic definition of the microgrid. Basically, it is a localized grouping of electricity sources and loads. Uh, Normally, it will operate synchronism with the main grid. Sometimes, if something happens in grid or some planned interruptions, it can act as a standalone system also. But when coming to microgrid installations, most of microgrid installations are standalone microgrids, especially due to the application in that area. This is the basic architecture of a microgrid. Here, if you have your different energy resources like solar, wind, biomass, uh, and your battery storage systems, and different loads, maybe the residential or agricultural or industrial. like different loads you have. All are connected in a microgrid, and at a single point you can see a synchronization switch here. At a single point it is connected to your utility grid. So you can complement the utility grid, or you can isolate from the utility grid and work in a standalone mode. That is the basic architecture of a microgrid. So there are different schemes of microgrid based on your application. You can have a DC microgrid. So you can have different energy resources like solar, wind, your fuel cell, battery storage, or even diesel generator, and everything can be converted into DC, and you can have your loads in DC side, and also with a single point you can connect it to the utility grid. Such an architecture you can take it as a DC microgrid. Even you can go for a low voltage DC, 48-volt DC nano grid or something like this. And also you can have a DC centralized AC microgrid. In that case, your loads will be in AC sites, but your resources, everything you will convert into DC, and a single point you will convert into DC to AC, and your all loads will be in the AC domain, and obviously you can have your utility interconnection. So these are the different some of different architectures you can select according to your application and your availability of the resources. This is one of the microgrid scheme we implemented in phase 1. It is in West Bengal, Jammu, Sundarbans, Laushni Island. There we have different resources like solar. Solar we have, and a small wind electric generator, and some there are biomass plant also there, and battery backup also there. So we made the power electronics interfaces for this energy resources. We can we made the basic interface modules. We term it as basic interface module, that BIMs. Then we everything is parallel in that AC side with the help of a central control unit, because everything is coming to a common control room. If everything is coming to a common control room and your all power electronics interfaces are in a common control room, then you can easily go for a centralized control unit for a supervisory operation of your different power electronics interfaces. So this is also one architecture. If it is if all the energy resources are not coming to a common control room, you may not go for a centralized control unit. So here we have a flexibility of using a centralized control unit for providing the command for power sharing between the different energy resources. So as per the application, the architecture derived was like this. So why we are going for a microgrid? These are some of the architectures. This is not limited to these architectures. You can, as per your requirement, you can make different architectures. Actually, these all are evolving things. So you can add your own things, your own technologies, topologies, everything. So basically, why we are going for a microgrid? Actually, when it demands a reliable energy source for your critical infrastructure, like a campus microgrid or a defense microgrid, if your critical infrastructure needs a quality power system, then you can go for a when after a natural calamity or something, or a collapse, if you want to easily restore your power grid, then the national grid may not be stored such easily. So such localized microgrids can restore easily. So the resilience is a point in selecting a microgrid. Then I initially told microgrid is all energy sources may not be uh, green power sources. You can have fossil fuels also in a microgrid, but if we are using more energy resources like solar, wind, or other renewable energy, then we can introduce more green power to our conventional system. Then it can always complement your main grid, even with conditioning things. A microgrid can provide grid conditioning like things, especially in during the peak demands. So that is also an application. Then another important thing is it enhances social well-being. Like when coming to a rural electrification, there are so many areas in our country where electricity is still not reached. So in the case of rural electrification, you can well use your microgrid architecture. Uh, that's why initially I told most of the microgrids are installed or especially for the rural electrification. So most of them are standalone microgrids. So because these are installed in areas where our national grid cannot penetrate. So I will focus on one of such application in one of our cases where we installed a standalone microgrid at Marayur. These are the requirements of a microgrid, need for a microgrid. So you can classify your microgrid into different things, like its operation. Based on its operation, you can classify it as an off-grid microgrid, or if you are complementing a big microgrid, big grid. What we define as a big grid is a grid with frequent interruptions. If your microgrid can work together with a big grid, you can term it as a big grid supporting microgrid, or obviously for green energy penetration into the grid, you can use a grid connected microgrid also. So based on its operation, you can classify it as an off grid or weak grid or grid connected, and again based on its application, you can again classify into different categories like residential microgrid, uh, remote microgrids, and industrial or commercial microgrids, or it is for defense application. You can have defense microgrids and even urban microgrids, and institutions for institutions and campuses for your labs and all. You can have uh, campus microgrids, even uh, for houseboats and all thing. You can have AC/DC microgrids for small AC/DC microgrids for such tourist application. Again, you can have the concept of interconnected microgrids. You can interconnect your different microgrids, nearby different microgrids, and you can share the power between the microgrids. That is optimal utilization of resources may be taken place in such cases. So these are the different classes of classification of microgrid. I already told these were things. This is old data in 2018. Actually, the most part of the world microgrid installation is in North America, and in about 34% is in North America, and about 40% is in Asia Pacific. Especially in this Asia Pacific, most of the installation is in Japan, I think. So for a quality power system, they are uh, introducing more microgrids into their main grid. And also you can see this data. About 39% of the world's microgrid installed is that percentage wise it may change. Anyway, a major part of the microgrid installation belongs to the remote microgrids, uh, especially such microgrids have direct application, that is direct electrification, or directly you can change a community with such microgrids. So the large percentage of the world's microgrid installation belongs to the remote microgrids. Then another large portion goes to commercial or industrial microgrids. Now I'm moving to one of our microgrid installation. This installation we have done in Yambet phase 2, which is supported by NIT, a nodal agency of MNRE in Kerala. And the location what we are identified was an off-grid tribal colony. It is near Munnar in Idukki district of Kerala. Here they have about 25 houses, about 100 of people living in that area, and it is 4 to 5 kilometers away from the Marayur area. That is, it is 4 to 5 kilometers inside a forest. Actually, we don't have much transportation facility there. Only four-wheel drive jeeps are available for the material transportation. Actually, why I am telling all this terrain specific details is this is selection of our power electronic system. Even it will depend on this like terrains. So the scheme developed for the particular installation was like this. We have and we surveyed the location. There is a possibility of solar installation. So our major source, primary source, power source was solar, and we have a power conditioning system. All our indigenous systems we installed there. This is the scheme. The major source is 25 kilowatt solar PV, and a 15 kVA diesel generator is also there, and a 360 volt 300 Ah battery bank also installed in the control room. These are the major energy resources what we used in the installation. We classified, actually this is an off-grid location, and we classified the houses as into three categories, and each phase, this is a three-phase system, so each phase connected to each clusters. Actually the 230 volt AC connected to each house to every houses. And for street light application, we use low power LVDC, low voltage DC architecture for powering the control room and the street light application. We have our own LVDC architecture, so we use that LVDC system for providing the street lights. In such a tribal settlement, street lights will be an added advantage, like it will save them from elephant attacks. And also we have the facility for water pumping, and we have the power conditioning system is for supporting the solar power telecom power also, but the telecom tower was not there. So still, this is the architecture, and these all things we can support using this uh, installation. The major features are a 25 kilowatt solar PV as primary source, 30 kilowatt indigenously developed power conditioning system, then 360 volt 300 Ah battery storage, and LVDC based street light application. Then we also introduced indigenously developed smart energy meters. You may think whether a smart energy meter is uh, needed in such a tribal location. It is not for building application. As a technology showcase, we have installed different technologies developed part of NAMBET in this case. Then actually in such terrain we cannot go for overhead lines and all. So underground UG cables are used for the power distribution. So it was a challenging work there. These are the specification of power conditioning system. This is the basic power hardware schematic. Basic power hardware. Uh, what we previously told, we have used a basic interface module like this. What we call it as we are calling it as a universal front end because it can interface with either AC or DC. So in both ends, in the input DC end and in the AC side, in both sides, we have the same module. Same module is there. In the when in
Yep. Sorry, sir, you are not audible. Sir, you are not audible, sir.
hello, can you hear now?
Yes, sir.
Can you hear?
Sir, now you are audible, sir.
Okay.
So previously, sir, these slides are also not moved. Now I think you are at the 20th slide, no, sir, now?
I will just move.
Our schematic.
This is during this time it was audible.
Yes, it is audible, sir. Now it is audible.
Not now. During this slide, it was audible, or shall I continue with this slide?
You can continue. You can continue.
Okay. Actually, this is the power hardware which we use for the interfacing the energy resources. We call it as a universal front end because we can either interface AC or DC with the same hardware. In one end, when we are interfacing AC, DC, it will act as a interleaved boost converter, and other side it is connecting to grid, or either you can connect to your grid, or you can work as a standalone system, standalone inverter you can work. And this is our isolation was in AC side, that 50 hertz transformers are used for the isolation. This is the basic architecture of the basic interface module. Rated power is 10 kVA. DC bus rating is 400 volt, and we used IGBTs and IPM for the stack. We have protections, hardware and software protections, like different DC and AC or voltage or current temperature protection is there. Our switching frequency is not 5 kilohertz, it is 10 kilohertz for the system. These are some of the modules used for basic interface module. Then actually in this architecture we don't have a spare converter for interfacing the battery. Actually, what we done is we rearranged our grid connected inverters for the microgrid application. So we don't have a separate converter for battery integration. So what we done is the battery is interfaced to with DC bus side. So in this case, you have flexibility of not using a dumb load. In this case, you have every time you will be having a load at your DC bus for this boost converter. And this is the basic architecture for in the interconnection of battery what we used. In this case, we can avoid a separate converter, but it is having its own merits and demerits. So the battery used is a maintenance-free battery. Batteries from Firefly. The capacity was we have used 3 sets of 360 volt 100H battery, so that almost about more than 20 hours it will work from both solar and battery. About 20 hours it will work, more than 20 hours. This is some basic about battery charging. What we used is a lead acid battery. As it is a standalone application, we no need to go for a lithium battery, which is little bit costlier than lead acid. So we went for a lead acid battery. Everything selection like batteries, everything will depend upon your application and your needs. So we went for a lead acid battery. But then these are the basic charging and discharging cycle of charging requirement of a lead acid battery. There are three parts in the charging of lead acid battery. First is constant current mode, where you can charge up to 70% of the battery. It will be in constant current mode. Then remaining 30% you can charge by topping charge, that is in constant voltage mode. You can maintain the battery charge also with that float charging. This is the curve of the battery charging, and from the even with the battery VOC, you can identify the percentage of charge available in your battery. Uh, if before measurement you can have, if you have a sufficient rest time, then from VOC itself you can identify the percentage of charge. This is the approximate VOC of for 12-volt battery and the percentage of charge available in your battery. Uh, Actually, as it is not a grid connected system, our our aim is to charge the battery in in uh, in the in this different charging methods, and also we have to provide the electricity to the settlement. So uh, there is especially no need for a MPPT. So we use an optimal current tracking method for battery charging, and also for providing power to the settlement. That is, as there is not grid connected, we may not go for a MPPT, but sometimes these two things will match. This is the uh, architecture we followed in the development. Then actually for our power conditioning system, we have three beams. Three beams means we are in need for about 36 PWMs. Uh, so at that time, what we used is TMS 320 F2812 power products processors from Texas Instruments. So we can have a 12 PWMs from each DSP. So it is not sufficient for our application for running the complete three beams. We are in need for about 36 PWMs. Then we went for a FPGA core processor also. In this case, we have two DSPs. This is our digital hardware. In this case, we have two DSPs and one FPGA. First DSP will acquire all the ADC signals, that analog and signals. Every measurement will be taken care by first DSP, and algorithms will be running in first DSP, and the reference signal will be given to FPGA. Then all the 36 PWMs will be generated from the FPGA, and here the second DSP we are specially using for its user interface application, that is graphical LCD interface, then remote connectivity. For such things, we are using the second DSP. So this is the architecture of the digital hardware which is used for the uh, implementation. This is a photograph of the digital hardware. You can see two DSPs and one FPGA. There are four external ADCs. All are simultaneous sampling ADCs, each having 8 analog inputs, analog channels. Also,
Sorry to interrupt you.
tell me, sir.
Not moving, sir. Please select that corresponding slide, sir.
Hello?
Sir, I think you are in now which slide, sir? Because slides are not.
I am in here. I am in 26th slide.
26, but we are able to see 20 to 23, sir. Please select the 26, sir. Otherwise, sir, could you please start sharing once again?
Yeah, that I can do. That I can do. Now, which slide is coming?
Now screen sharing is not starting.
Let me check. Now, which slide is coming?
Now 26 one, sir.
Okay. This is our.
Sir, can you try with double clicking that slide, sir? Can you please try with double clicking? I think sometimes it will not take in the Teams. That slideshow, please click 2 times, sir. The slideshow bottom.
Actually, this is a slideshow in my PC. I think that's.
Okay. Oh, okay, sir. Then no problem, sir. Please continue, sir.
Once more, I will try.
Sir, even while sharing, you can try with window sharing option also, sir. 2 options are there. You can try with another mode also. I think that might solve this problem.
Yeah, actually, but I cannot share the entire. Let me check. Now, is it in full
Yes, sir,
screen?
now it is in full screen, sir.
Okay. Previously, I was not able to share the entire screen. I was in Windows sharing. Now it's okay, no?
It is okay, sir. Just click on the hide options. Hide. On this screen, we are able to see that Teams Microsoft.com is sharing. Please click on that hide. That will not appear for us.
Okay, let me go. Now it is 26 slide, no?
Yes, sir. 26 one, sir. Digital hardware. Just please click on that hide, sir. Hide option. On the screen, I think you are you able to see it, sir? That
that hide.
hide. Yes, sir. Now it is perfectly, sir.
It's okay. Okay. Thank you.
Please carry it.
This is our digital hardware we developed for the for electronics interface. You can see the 2 different DSPs, and this is FPGA, and we have simultaneous sampling ADC, each having 8 analog channels, and these are external PWM interfaces from the FPGA. We can either go for electrical interface or optical interface. In that case, both are available in this card. These are some details of the DSP and FPGA. This is the basic control architecture. It is in this one. It is in grid connected mode. We will use a MPPT controller, and the voltage controller will. We have a predictive digital current program mode, which produces the duty cycle requirement for the interleaved boost operation. This is the basic architecture of the controller what we used. And this is a power hardware developed in our CDAC lab. You can see this one is power condition system with 3 beams and associated filtering circuits. And also another box you can see here. It is 50 Hz isolation transformers. So as it is a isolation is in 50 Hz, it is a little bit bulky. Here comes some waveforms related to our testing activities. And another technology we use in the microgrid installation is for 48 volt architecture, DC architecture, LVDC architecture for control room powering and our street lights. This is one of the street light installed at the site, and these are some photographs from our lab where we are using the 48-volt DC loads for lighting, fan, then even air conditioner also. This is the basic architecture for the 48-volt DC. It can either work from the solar. It's a MPPT charger is there, and also battery backup is available in here. And also, if both are not available, even if we don't have a solar, then also we can uh, charge the battery from the AC supply. The Roshan is there. So this is the basic architecture in that LVDC thing. Even these all things, even with you can add wireless connectivity with Bluetooth or wireless Wi-Fi to the LVDC, and you can control your appliance like that. Then another important thing we used in the deployment is smart energy meters. These are smart energy meters our, developed in our CDAC. We have transferred the technology for smart energy meter to different TOT partners, about 7 TOT partners. We transferred the technology, and some of them are now in the phase of testing the meters. So basically, a smart meter, what it is doing is there will be a bidirectional communication between the user and the utility. So that is the possibility with a smart energy meter. In the case of our microgrid, uh, we used it is for showcasing the smart meter technology, and also we used it for monitoring of the microgrid, because with the smart energy meter, you can have different connectivities like Bluetooth and wireless Wi-Fi connectivity, and you can read data from smart meter with a Android tab or something. So for your system monitoring also, you can use the smart energy meter. And also there is a possibility of remote connect disconnect option. We can disconnect loads from the microgrid in AC site. That also possible with the smart meter. For both this application, we use a smart energy meter in this microgrid. This is sample monitoring screen with smart energy meter, and this is a LVDC powered TV, which is used for monitoring purpose in our site. Then we also have remote monitoring facility for our power conditioning system. This is basically what we are using is in every microcontroller or DSP we are using for power electronics interface. You can have a basic serial communication like UART and all. So with utilizing that basic serial communication, you can connect some your Bluetooth module or Wi-Fi module and interface it to some tablets or PC. So, and with utilizing that tablets and all, you can post data into internet and to your server, and you can remotely monitor, and also you can control. You can pass control signals. Uh, in a administrative login, you can pass control signal to your remote microgrid or conditioning system. That is the basic functionality of remote monitoring what we used in our microgrid deployments. This is the sample screens uh, where we for displaying the parameters. So some of the basic protocols, communication modules used in this PCU development is, one is very important, this CAN. This CAN module is used for data exchange between different digital hardwares and the different DSPs. So for providing the uh, current command or power sharing, you can better use the CAN modules. It is very it will work in a rectal environment. So this is one of the basic communication interface used in such type of applications. So you can move up to a maximum baud rate of 1 Mbps within a 40-meter distance. So this is the basic frame of a uh, CAN protocol. Up to 8 bytes of data you can communicate within one frame. And obviously for this communication and remote monitoring interface, we are using the basic serial communication like UART. This some of the field deployment photographs. You can see the rocky area, which is not utilized, unutilized land, which we use for construction of the control room and installation of solar panels. There was a natural south inclination for that rocky area, so we selected it for installation of solar panels. And we also developed a control room there for housing all this power conditioning system, battery bank, and diesel generator, everything. This is our control room, and this is the solar panel installation. These are some photographs of the field deployment. You can see the power conditioning system under testing. This is photographs taken during the testing, and 3 sets of 360 volt 100 Ah battery, that also you can see. And this is our street light, LVDC based street lights. Then smart energy meter installed at site. There's diesel generator for backup operation. Then you can better you can now you can see the houses that houses which were in that tribal settlement. All are not good houses. Uh, Mostly hutman houses. You can see that houses. So after the deployment of microgrid, how it is impacted the social life. Initially, I told almost a big percentage of microgrid installation in the world belongs to the off-grid microgrids, especially for such a remote places. So how it is impacting their social life. You can see the photographs after the installation of our microgrids. They used uh, that electricity for construction purpose. Even during our installation, we face very much difficulties in constructing a control room there. Everything is man-made things. Manpower is used for every thing. Now for the construction itself, they are using the electricity available from our microgrid. So now they have flexibility of using some cutting machines and all. Then after installation, some of houses they purchase televisions. Actually, they never thought of getting electricity uh, in the near future. So they are so excited to have the electricity, and their festivals become more colorful. And also even for cooking also they used uh, this is the microgrid power. So there is a change in the attitudes. There is a change in the social well-being, and you can see the houses. This is from the previous photographs. You can see what was uh, their houses were like, and this is the first house uh, constructed there after installation of our microgrid. So it is something similar to what we are making. So before during any construction, they were not providing any points for power points, anything. Now they are providing the points for the fan, ceiling fans. So there the barrier barrier was non-availability of non-availability of the reliable energy source. So there is a direct impact of the microgrid for changing the social life. So there is a change in their perspective, change in their lifestyle. Then their community is transforming slowly, and also during the COVID time, they used this uh, this is electricity for their online studies. So there is a direct social impact for such off-grid microgrid. Then I can show a small video. Let me check whether it can play it or not. Can you see?
Yes, sir. Yes, sir.
Can you see video?
Yes, sir. We are able to see. Please, sir, please increase the value.
Can you see video?
Yes, sir. We are able to see, sir. Please increase the value.
Hello.
Yes, sir. We are able to see, sir. Please play it, sir.
Okay. Actually, this is the location where we install the microgrid. These are houses. The transportation and travel was very difficult. You can only go with a four-wheel drive jeep and all. So the transportation of materials, air conditioning systems, everything was very difficult. This is the control room. This is the LVDC rack for 48-volt system. This is the power conditioning unit for Rourkela. I hope now you can see the PPTs.
Yes, sir. It's visible, sir.
Uh, Now I'm going to our another microgrid installation. That is before what I explained is a completely off-grid microgrid. It is for a completely off-grid location. Now in number phase three, we have started the installation of another microgrid, which is capable of operating in both grid connected mode. Especially, we are aiming for a weak grid, a grid with we have identified a location with frequent interruptions, and that installation process is ongoing. So, what we are added is we are adding a multi-layered microgrid manager for asset management. So sometimes when it is coming, it is complicating. Your power electronic systems, standalone power electronic system may not work as a microgrid. You may have to add the intelligent microgrid managers and controllers uh, for the optimized controlling of your microgrid. So from the scheme, you can see there are different energy sources and uh, and different loads. And now we are adding a multi-layered microgrid manager to the microgrid system. And this is obviously interconnected at a common point to the grid. This is the basic scheme of the microgrid. What the installation is in process. We are implementing it is in the Elephant Rehabilitation Center, Kotur, Trivandrum. Uh, Kerala Forest and Wildlife Department is supporting us in this uh, location-wise installation process. So the major features are 20 kilowatt solar PV and 200 Ah 400 volt battery bank, and we have intelligent microgrid manager and DG backup, and obviously the LVDC powered street lights. And what is a microgrid manager? Basically, a microgrid manager selects the operational modes of microgrid. This is from IEEE standard 20307.7 2017. It is the IEEE standard for the microgrid manager. The operation of microgrid in grid connected or islanded mode. It is selected by the microgrid manager, and it enables the automatic transmission of different modes, that is grid connected and islanded mode. It is facilitated by the uh, microgrid manager. Either you can do a forced isolation, or you can schedule a interrupt, or based on your grid conditions. Also, you can isolate your microgrid. So these all are possible with the microgrid manager. Then a resynchronization of microgrid with PIT also managed by the microgrid manager. So these are the functionalities of a microgrid manager. When it is coming to a commercial terms, it is uh, the it can also support in the market evaluation and market integration of the microgrid. So basically, it's a multi-layered architecture. We have different levels. At level one, it is a lower level. Uh, the control in this lower level, it can work voltage and frequency control, like group control, and it is basically of the controls in uh, your power conditioning system and all. Then next control is core level controls. This is defining the transmission and dispatch functionalities, that is connection disconnection from the main grid. It is controlled in level 2. In higher level, it is a supervisory kind of control. You can communicate to the SCADA system or some communication standards may be incorporated in this third level, and this grid market, the commercial aspects, everything is the part of the third level. This is the basic architecture of a microgrid controller. This is the functionality of microgrid controller from the IEEE standard. Uh, you have the lower level functionalities and the instrumentation, then dispatch and transition controls, and at a higher level you have your forecasting and optimization like things. Then the power architecture. The power architecture selected was, what you can see is here, for interfacing the solar, we have two DC-DC converters, and interfacing the battery, we have a separate DC-DC converter. And this DC-AC inverters, this is a single thing. And our digital controllers is controlling all these activities. And as it is a microgrid, it can either system should either work from 230 volt AC or some battery power. For continuous, you have to enable a continuous power supply for your controllers for microgrid. So this is the PCU level architecture. In this total line, you can see the PCU like PCU type architecture. And from HMI, we also have a HMI, that is a visualization, so visualize graphic LCD visualization, and also as a part of HMI, you have a communication. You have to communicate your parameters to a microgrid manager in this case. So you have a microgrid manager, either like the based on the complexity of the microgrid, you can go for a single board computers like Raspberry Pi to uh, and high-end servers for your microgrid manager. So this microgrid manager controls the grid connection and disconnection operations in this case of microgrid. Here also you can have a critical load and non-critical load selection. When it is working in a standalone mode, uh, based on your power condition, you can uh, go for a you can either isolate your non-critical loads when your power levels are reducing. So that possibility is also there in this microgrid. And even you can have a PMU distribution PMU based control of grid connection synchronization. It is not realized, but there is a possibility of using PMU data for this grid disconnection and synchronization. So this is the basic for architecture, complete architecture of the system. And coming to the power module architecture, in the previous video and all, you have seen the terrain specific difficulties in transportation of the uh, huge power electronics modules, that diesel generators and our transformer panels, and everything was very difficult. So after that, we thought for a reduced form factor system. So what we selected is in previous module, what we are having is we have isolation was at uh, 50 hertz side, that AC side. We had the isolation, and so obviously that will be bulky transformers. Uh, but it has its own merits, like during a fault, that transformer can provide a fault impedance. But especially when we're thinking about a remote location, the form factor should be reduced. So in this thing, what we selected is uh, uh, high voltage isolation topologies. that is high frequency isolation topologies. Now the 50 hertz isolation is going to high frequency side, that is about 50 kilohertz side isolation. So magnetics components are reducing. So such a topology we selected. Dual active bridge topology for DC-DC converter is selected. Then for the solar and battery, we are using a dual active bridge based DC-DC converters. And at inverter side, we are using four-wire, three-phase four-wire inverters for handling the unbalance during a standalone operations. So this is the basic architecture of power modules. Now you have the flexibility of using wide bandgap devices like silicon carbide devices. So it is easy to go for a 50 kilohertz or 100 kilohertz operation. Previously with IGBT and IPM, with you can go up to 20 kilohertz. Even some specific IPMs, you can further frequency can be increased. But now with the flexibility of SSC modules, you can go for a high frequency operation. So for our particular power conversion, the SSC frequency selected is 50 kilohertz. Uh, so we have a modular dual active bridge. You can either connect your solar or battery into that DC-DC converter, and obviously we have a digital hardware for controlling all these DAPs and power inverters. This is the basic architecture of power modules. Basically, I'm not going to the control part of dual active bridge converter. I will just brief introduction to dual active bridge converters. Here it is a bidirectional converter. The same topology you can use for a battery charging in microgrid. Also, you can use for a battery charger in electric vehicles. Even in that electric vehicles, the same topology you can very much utilized. Uh, so this is the basic architecture of dual active bridge converter. You have a high frequency transformer. In our particular case, it is 50 kilohertz transformer, which is providing the galvanic isolation between the AC and DC. And you have symmetrical H bridges in both sides of the transformer, and inductor for power transfer inductor. This is the basic basic components in the dual active bridge. And for power switches, we are using SSC based modules so that we can easily operate at 50 kilohertz. So basic principle of the dual active bridge converter is basically our power transfer equation. That is here V1 if you have a magnitude and angle, and location V1 you can you are having an magnitude and angle. Then the basic equation controls determines your power flow is this is V1 V2 sin delta or sin phi by its impedance. So the basic equation is utilized in the dual active bridge also, because in this side it is a AC with square pulses. So you can have a phase shift at its primary and secondary for power transfer. For the bidirectional transfer, you can appropriately adjust the phase shift between primary and secondary. So this is the basic fundamental principle of a dual active bridge converter. So with a dual active bridge converter, you can reduce your form factor easily. Uh, You can just see the waveforms. Here you have two switching waveforms. Basically, for controlling a dual active bridge converter, you can go for different modulation technique. Most commonly, single phase shifted PWM techniques. You can either go for dual phase shifted or multi things. But it is easy to implement a single phase shifted PWM in case of dual active bridge, and also you may require less number of PWM in that case. So both pulses operates in 50% duty cycle in this case. Then the phase shift determines the power transfer between primary and secondary. So here you can see a phase shift. Uh, Actually, this is the yellow. What you are seeing in yellow is a primary side, and in the secondary side, that pulse is you can see in green. So this phase shift between these two determines the power transfer. Our switching frequency is 50 kilohertz in this. You can see here. So in bottom you can see two waveforms. Here you can see a much higher phase shift when it demands a more power flow. Then uh, now in second waveform you can see very small phase shift, that is in the fraction of angle, that is less than 1 degree, less than 0.5 degree. You can see here in that case of less power demand. So this phase shift determines the power flow between primary and secondary. So this is the basic operation of dual active bridge. Here what you are seeing is uh, transformer primary and secondary waveforms of a dual active bridge. You have to carefully address your magnetic components in the case of dual active bridge converters. So in yellow you can see the primary, and uh, in yellow you can see secondary transformer waveforms, and this is in green it is transformer primary. So this is the basic waveforms of 50 kilohertz frequency. Then this is waveform of actually I told we have two dual active bridges for uh, solar. We are using two modular dual active bridges for the interfacing of solar. So this is a parallel operation of two dual active bridge converters. This is these two are the current waveforms. And when coming to inverter side, as our inverter need to work in a standalone mode also. In standalone mode, we need to control all the loads, all the loads connected to the system. Uh, we don't have a grid, so there is a huge possibility of uh, occurrence of unbalance in that case. So it is better to use a three-phase four-leg inverter for better handling of the unbalance. So a 25 kilowatt inverter we have developed this also with SiC modules, having a LCL filter at the grid side, and operational frequency is 50 kilohertz also in this case also, and a proportional resonant proportional resonant controller used for the control of the inverter. This is basic thing about our inverter used in this case. When it comes to a standalone three-wire operation, uh, what you are seeing in left side, it is a standalone three-wire operation of the same inverter. Here, uh, unbalanced load is connected to your inverter, and you can see the waveforms, unbalanced in voltage waveforms in this case. And in right side, what you are seeing is a standalone four-wire inverter with a neutral switching. The same unbalanced loads are given here also, provided here also. Now you can see the almost balanced voltage waveforms here. This is the basic difference with the standalone three-wire and four-wire operation. So in the case of handling the unbalances, uh, we are using for a three-phase four-leg inverter for our microgrid topology. These are some of the test waveforms. And, you can see the RYB and uh, current Y-phase current here in green. Then another thing is grid connection of the inverter. What previously shown is standalone operation of the inverter. Next, uh, that microgrid also need to be addressed grid connected operation. This is grid voltages. Actually, I am testing in a IT park. In Toronto, we have two offices for CDAC. One is in Toronto Techno Park. There is an IT park. Uh, Actually, some disturbed waveforms. Here we are getting grid waveforms. You can see these are voltage waveforms of grid, and this is this one is blue is grid, and yellow you can see the generated reference for grid connection. This is a fundamental thing for grid connected operation of the inverter. Then uh, we have developed a new digital hardware based on a TMS 320F 28379D floating point processor for our new power hardwares. Uh, for our all of our previous power hardwares, we used then that time most reliable power electronics processor. Still also it was one of the most reliable processor F2812 from Texas Instruments. Uh, Now we have floating points processor for power electronics applications are available. Uh, F28379D, you can better utilize this floating point dual core processor for your power electronics developments. In this DSP, you can have a 12 sets of PWM. In our this particular case, we have three dual active bridges and a four-wire inverter. In that case, we are in need of a 10 sets of PWM. So a single DSP with a single DSP, we can handle the entire system. In this case, we also have a FPGA coprocessor when it comes to a very intense control application. We can use this Max 10 FPGA, or this is a powerful FPGA for as a coprocessor for controlling the complete system. And also in this system, we are using a 8-channel simultaneous sampling system with ADCs for analog data collection. So this is some basic about the digital hardware developed in CDAC. Here, your DSP this DSP is having dual core. One core you can use for communication also. In our particular case, we have a HMI, and that is communicating with microgrid manager. So we are definitely we were in need of a communication interface. So in this dual core, with one core, we are producing all the PWM signals and control signals, and second core is dedicated for user interface and communication with the microgrid manager. Now this is the PCU developed at CDAC lab. It is a proper unit developed at our lab. You can see these are gate drivers and devices, and now that transformers and inductors are magnetic parts reduced to a small form factor as it is in 50 kilohertz. We have a graphic touch screen LCD with graphic touch screen HMI with storage option. This is actually in both cases. In previous case, this is the power conditioning system we used in our previous installation. This is a transformer with transformer design. Isolation was at 50 hertz. So obviously there will be a bulky transformer, but it is having its own merits in the case of fault isolation and all. So and also this is with silicon IGBTs and IPMs. Now the same capacity is reduced to small form factor with silicon carbide, utilization of silicon carbide technology and high frequency isolation. In this case, we are especially aiming the remote locations. When our microgrid is going to install at remote locations for the transportation and carrying purpose, this reduced form factor PCUs will be well utilized. So what I'm trying to telling is everything is depend upon your application. So in the remote locations, our concern was transportation things and all. So it should be in reduced form factor. So actually, I told when when it comes to a complete operation of microgrid, it is not only a standalone power electronics box. You have to add multi-layer controllers and supervisory controllers to your microgrid power electronics thing. So microgrid manager is in our case microgrid manager is taking care of this part. That is this is the basic interface with microgrid manager. You have your microgrid manager with a customized protocol of it is derived from C37.118, which is used for PMU and wide area monitoring things. With such a customized protocol, the microgrid, the PCUs or conditioning systems will communicate with the microgrid manager, and microgrid manager can utilize this data for visualization and asset management. Is the screenshot of intelligent microgrid manager. Very first thing is visualization. You can interface different PCUs, PMUs, LVDC things, etc. to your microgrid manager, and you can have visualization of voltage, current, power, and everything, and the operational modes, and if there is any fault, anything is there, that also will be displayed in microgrid manager. This is the primary application, and with a administrative power, you can select the operational modes in case power scheduling. If it is operating in a standalone mode in a with a battery, So even you can schedule your power for daytime and such things. Such all things you can whether it should be non-grid or off-grid, everything should be if any scheduled isolation, all such things can be uh, controlled with a microgrid manager. Uh, so these are some of the examples we learned through the practical implementation of microgrids in different Yaml projects. Actually, we have another project is ongoing, that is interconnection of microgrids. In such things, we are in that project. We are installing another microgrid layer to our previous microgrid at Marayur, and we are interconnecting these two microgrids. I think that was the first try in our country for interconnected operation of microgrid. Uh, then uh, in that case, the optimal sharing of resources uh, will be ensured by the interconnected operation of microgrids. In that case, we are using a central microgrid manager for controlling the entire microgrid system. Uh, I am concluding the presentation here. Uh, I'm happy to share some of our experiences. It may not be the fully optimized thing, but it is based on our expertise, our time requirements, and uh, project cost. Every factor have to taken care in selection of power electronics things, its switching things, magnetic components, even the availability of the magnetic components. So selection of the hardware or power electronic system, there is there are, I can say, there are technical and non-technical things. So I am happy to share our experiences with you. I am concluding my presentation now. Thank you very much. Hello.
Sir.
Yes,
Yeah.
sir.
Yeah, and now I concluded my presentation. Actually, I have a travel afternoon.
Okay,
So,
sir, no problem. So from the
very-
participants saying
So there is a query in the chat box. The participant can mute your audio and you can interact with the sir. Is by Mr. Veerasundaram, sir. Sir, can you unmute your audio and speak? Arul, sir, let me read the question for you. How to diagnose faults with microgrid system for research purpose?
uh, actually, in this case, our hardware, that is our PCUs, we have uh, different protection and PCBs, and we are logging different faults uh, which is occurring in our system. So in that case, we are using some hardware faults. Some in case of some faults, we have to uh, switch off. Not switch off. We have to block our pulses. In that case, in some priority faults, we are using some hardware protection. We also have some software protection in our power conditioning systems.
Any more queries from the participants? If you have any doubt, you can interact with the speaker. Sir, I think there are no more queries from the participants side. I think we can conclude this session, sir. Thank you, sir. Thank you for joining with us and sharing your knowledge.
Thank you, sir. So you are giving your valuable time to us. So for delivering your lectures and some demonstrations, that is, I think, is very important current scenario how to develop the products. Okay, so that can also encourage us to planning and development of products. Okay, so heartily thankful to you for your valuable session to us. Thank you, sir.
Thank you very much for uh, giving the opportunity for interacting with the community. Thank you very much.
Thank you.
Shall I
Yes, sir.
exit from the?
You may leave. Yes, sir. You may leave the
Yes,
meeting.
yes, you can, sir.
Thank you very much. Yeah, thank you.
Thank you.